Hi everyone. Today in this lecture I want to talk about two-port circuits. Previously, in our previous chapters, we talked about Thevenin and Norton equivalent circuit. In Thevenin and Norton equivalent circuit, our focus is on one pair of terminal. So the focus is on only one pair of terminal. For example, we have this circuit. This is our circuit, and we want to know what is the equivalent of this circuit from this particular pair of terminal. Let's call this pair as A, B terminal. So we can focus on this pair of terminal, and then we can describe the equivalent circuit in form of Norton or Thevenin equivalent. Now, today in this lecture, I want to talk about two-port circuit. Thevenin and Norton equivalent that we discussed previously in previous chapters and 211 is basically a one-port terminal because our focus is only on one pair of terminal. In two-port terminal, we are focusing on two pairs of terminals. So the first feature of a two-port circuit is that it focuses on two pairs of terminal. One pair is going to be input pair, and the second pair is going to be your output. So we have one input pair and one output pair. So this is how the circuit looks like for a two-port circuit. This is our circuit, and we are focusing on one pair here and another pair here. In first pair, we can add our input, so we can choose any input to be connected to this pair, which I'm gonna call it as A and B, and then the other pair will be considered as our output, so I'm gonna call this as A prime, B prime. So we can measure the output here, and we can connect our input to the first pair of terminal. So this circuit can be considered as a two-port circuit. In a two-port circuit, instead of focusing on one pair of terminal, our focus is on two pair of terminal. And there are some features that we have to consider in a two-port circuit. The first one that I want to mention is that a two-port circuit does not have any energy stored. So if you want to be able to model this two-port circuit, we have to make sure that there is no energy stored in the component inside the circuit. The second feature of the circuit is that there should be no independent source in the circuit. So we're not allowed to have independent source in the circuit if we want to model based on what I'm going to discuss here. So no independent source. The third feature that you should be aware of is that each terminal has a current. So for example, here I have I1 and V1, and on the other terminal I have I2 entering and V2. The third feature that you have to be careful is that the two-port circuit is a circuit that has exact same current into the port and out of the port. So if I'm assuming that here I have I1, then the same current comes out of the port here. So I1 enters the port and I1 comes out of the second terminal of this pair. Same thing happens on the other side. So if I2 is entering to one of the terminal of this pair, then the same current comes out of the second terminal of the pair. So I2 comes out of the second terminal of this pair. So this is an assumption that we are making here in order to be able to describe the model of this circuit. So I'm gonna write this constraint here. Now let's focus on terminal variables. So I'm going to draw it one more time here. In this circuit, we have two variables for the first pair and another two for the second pair. So I have V1 and I1 here, and the other pair I have V2 and I2 here. So I have 4 terminal variables. However, only 2 of them are independent variables. So I have only 2 independent variables. So it means that among V1, I1, V2, and I2, I can choose 2 of them to be my independent variables, and then the other 2 variables can be described based on my selected independent variables. So I have 4 variables, and I have to select 2 of them as my independent variable. So it means that there are 6 different ways of describing the model for this circuit. So here in this chapter, you're going to learn how to describe the model of a two-part circuit, and there are 6 different approaches of modeling, which depends on which parameter you are selecting to be your independent variable and which other 2 variable remains as your dependent one, in which you have to describe them based on your independent variables. Okay, so I'm gonna write those variables one more time here. So we have V1, I1, V2, and I2. So these are our 4 terminal variables. Now, I can choose the current to be my independent. So the first way is that I can choose my independent variables to be I1 and I2, and then my dependent variable would be V1 and V2. The second approach is the opposite of this one. So in second approach, my independent would be V1 and V2, and my dependent variable would be I1 and I2. So for now, I'm just showing you 2 different approaches of my selection. So I can choose my currents to be the independent variable, and then I can describe the voltages based on them. Or I can choose the voltages to be my independent, and then I'm going to describe the current based on my voltages. So these are the first 2 approaches of describing the circuit model based on my selected independent and dependent variable. In these approach, I'm going to work with impedance and admittance matrices. So let's focus on the first one. So here we are talking about our first modeling approach. Here I need to describe my dependent variable, which is V1 and V2, in terms of I1 and I2. So I need to describe them as a linear combination of I1 and I2, I1 plus I2. The question is that what is the coefficient of I1 and what is the coefficient of I2 here? And same thing for the second equation. And same thing for the second equation. I'm going to call these coefficient as Z because here the equation looks like the impedance equation. So I'm going to use Z11 here, Z12 here, Z21 here, and Z22 here. So what I'm doing here is that I'm describing my dependent variables, which are V1 and V2, in terms of I1 and I2, which are my independent variables, and I'm using a linear combination of I1 and I2. Now, if you ignore, for example, I2 in your first equation, then that's an equation that is describing the voltage in terms of current, and that's the impedance. Same thing for I2. If you assume that your I1 is 0, again, you are describing your voltage in terms of current, so that's something you can think about as an impedance. So here, we are looking at the impedances. Now, the question is that how I can find this Z11, Z12, Z21, and Z22. The equation should help you to figure out how to describe them. So if I'm looking, for example, for Z11, what should I do? So if I'm looking for Z11, it means that I have to assume that I2 is equal to 0. So I have to assume that I2 is 0. Then I have Z11 as V1 divided by I1. Now let's add the assumption that I made here. I made this assumption that I2 needs to be equal to 0. Now let's do that for Z12. For Z12, this time I'm going to make the assumption that I1 is equal to 0. So this time I'm going to assume that I1 is equal to 0. So it means that if I'm looking for Z12, I need to find the relationship between V1 and I2 when I1 is equal to 0. Let's continue here. For Z21, in order to find this value, I have to assume that I2 is equal to 0. So Z21 is equal to V2 over I1 when I2 is equal to 0. And finally, for Z22, I have to assume that I1 is 0. So it helps me to find Z22 here, which is equal to V2 over I2 when I1 is equal to 0. Okay. Now it's a little bit crowded here, so I'm gonna write everything in a table in my next slide. So here this table helps you to figure out what should be Z11, Z12, Z21, and Z22 according to this equation. Now, let me show you how you can solve a circuit. The first thing that you should be careful about is that you are solving this circuit in two different scenarios. What are those scenarios? The first scenario is that you need to have your I2 as 0. And the second scenario that you need to solve this circuit in is the situation that your I1 is equal to 0. So let me remind you about having current as 0. When the current is equal to 0, it means that your terminal, for example here, terminal 2 is open circuit. And here it means that terminal 1 is open circuit. So in order to find Z, which describe your voltages in terms of current, what you need to do is that the first time you have to make your second terminal open circuited, and then you have to find your Z11 and Z21 by finding these two relationships. And the second time you have to make your terminal 1 as open circuit, and this time you have to find your Z12 and Z22, which is basically the relationship between V1 and I2, and then V2 and I2. Okay, so this is how you can find Z matrix, and this Z matrix has Z11, Z12, Z21, and Z22, and it describes the voltage in terms of current. Now, here you can see that you have 4 different terms to define, but there is something that might help you. There is a shortcut. So regarding Z12 and Z21, they are equal as long as you don't have any dependent source in your circuit. So if there is no dependent source, then you can assume that Z12 and Z21 are equal. So you don't need to calculate both of them. Calculating one of them is going to be enough. Now let's do an example so I can show you how you can solve the circuit in this scenario. Let's look at this example. In this example, you want to see what is the Z matrix of this circuit. The Z matrix means that we need to calculate Z11, Z12, Z21, and Z22. And because there is no dependent source involved, then I know that Z12 and Z21 are equal. So I need to solve for Z11, Z12, and Z22. Okay, for Z11, you need to have V1 over I1 when your I2 is equal to 0. So if I2 is equal to 0, it means that in second pair of terminal, in my output pair, there's no current, I have open circuit. So the easiest way to show that is that I can remove this line. So this is basically my circuit. If I can assume that I2 is 0. So here I2 is 0 and I still have V2. Don't forget that I'm making it open circuit, but still there is a voltage across this 15 ohm resistor. So V2 exists, but there is no current involved in my output terminal. So now I'm looking for the relationship between V1 and I1. And obviously it means that I have to find the impedance that I can see from this terminal. So V1 over I1 from same terminal means that I'm looking for Z equivalent. So Z11 is basically equal to Z equivalent from terminal 1 when I2 is equal to 0. So let's solve this. It's equal to 20 in parallel with 5 plus 15, which is 20, and in parallel with 20, it's going to be 10. So my Z11 is equal to 10. The next one that I'm going to solve is Z22, which is easier. So now I'm going to go back to my original circuit again. And this time, I'm assuming that I1 is equal to 0. So Z22, which is V2 over I2, would be equal to, let's assume that I1 is equal to 0. So if I1 is equal to 0, it means that I don't have any current in terminal 1. And this time I'm looking at Z equivalent from my output terminal. So here it's Z equivalent from terminal 2 when I1 is equal to 0. So that's going to be 15 in parallel with 20 plus 5. And that's equal to 9.375. So now I can complete my Z impedance by replacing Z22 by 9.37. Now there is one more component that I need to calculate in order to complete my circuit model in form of impedance matrix. And that's Z12 or Z21. They are exactly equal. So I'm going to go with Z12. Z12 is equal to V1 over I2 then I1 is equal to 0. Okay, so let's go back to the circuit. So this time I'm assuming that I1 is equal to 0. So there is no current going here. And then I'm looking for the relationship between V1 and I2. So the voltage drop here, which is V1, and I2, which is entering from my output terminal. What I can do here is that I can divide I2 between 15 and 25 first. And then when I have the current which is going in this direction, I can multiply that by 20 to get the voltage drop across 20 ohm resistor. So the first step is that I'm going to divide I2 among 15 and 25. So let's do that here. So I'm going to say that the current of 20 ohm resistor is equal to a portion of I2, which is Z equivalent, divided by the impedance of the branch that I'm looking for its current, and that's 25. So over 25. What is the Z equivalent? Z equivalent is 15 in parallel with 25. So it's equal to 15 in parallel with 25, and we already know that's equal to 9.375. So here, if I put this number in my equation, I'm gonna have 9.375 divided by 25 multiplied by I2. Okay, the next step is that I have to describe my V1, which is the voltage drop across this 20 ohm resistor, in terms of the current that I found right now, and that's equal to 20 multiplied by that current. So V1 is equal to 20 multiplied by I20, so it would be 20 multiplied by 9.375 divided by 25 and multiplied by I2. If you simplify all these numbers, that's going to be 7.5 multiplied by I2. So it means that V1 divided by I2, when I assume that I1 is equal to 0, is equal to 7.5. So now I can complete my Z matrix, and I know that these two are 7.5. So this is the Z matrix for this two-port circuit, which describe the voltages of this circuit, V1 and V2, as a linear combination of I1 and I2.